In this tutorial, we will be discussing the differences between solids, liquids, and gases. Solids have a rigid shape and a fixed volume. The external shape can reflect the atomic and molecular arrangement inside, and we know this information reasonably well. Liquids have no fixed shape and may not fill the container completely. Instead, it sits at the bottom. And this information is not that well understood. Gases expand to fill the entire container, unlike liquids, and we have a pretty good theoretical understanding of these. Now these phases can change from one to another by changing the temperature or the pressure. Let's take a look at the differences between solids and liquids first. Notice that the solid keeps its own shape. It's not taking the shape of the container, whereas liquid does. It drifts to the bottom, and then gases then fill the entire container. We can go from a solid to a liquid by heating it up, or reversing the process by cooling it down. Now let's compare the liquids and the gases. Not only can you heat it up to turn it into a gas and cool it down to turn it back into a liquid, but if we change the pressure, that can also make those changes. Notice the amount of space between the molecules, unlike the liquid and the solid phases where there's not a whole lot of space between them. Because of this space, we can actually change the pressure between them. The pressure difference between the solids and the liquids aren't going to be that great, but the pressure difference between the gas and the liquid is rather large. So if we reduce the pressure, if we spread it out, we're able to change it from a liquid to a gas. If we increase the pressure, if we shove these things back together and we're increasing the amount the molecules are bouncing off the walls, by changing that pressure we can change it back to a liquid. So let's look at some of the comparisons between the three states, and we're going to look specifically at water. Please note that it's specifically about water and not all substances. Water is an anomaly. It's different than most substances. So let's first take a look at the density. The density of water is as a gas is extremely low, times 10 to the negative 4 grams per milliliter, or centimeters cubed. That's an extremely small density in comparison to that of the liquid and the solid. That's because the gas molecules are spread out. Notice that there's a big gap between these, whereas the gap between these molecules and these molecules down here for the solids and liquids are not that large. Now let's compare the liquids and the solids. Liquid is 0.998 at 20 degrees Celsius, where solid is actually smaller at 0.917. Water is one of the very few molecules that actually spread out when it becomes a solid. It becomes a crystalline. These charges that are found on the water molecules are making it into a very specific three-dimensional space, and they end up spreading out more than they do in the liquid phase. Therefore, because if we take grams over milliliters, the grams are staying the same. Because the milliliters are larger, the density is actually going down. We can look at a similar view of the molar volume. This is the volume it takes to have 6.02 times 10 to the 23rd molecules of water. It takes 30.5 liters to hold this many molecules of water, whereas it only takes 18 milliliters to hold this amount of molecules. Notice that the gas is in liters and the liquid is in milliliters. That means 0.018 liters. Notice that's way smaller in comparison for the exact same amount of molecules. Now if we look at the solid, just like over here with the density, the volume went up, 0.0196 liters to hold the same amount of molecules. Because it takes more room, that means that the density is going down. Finally, we're going to discuss the phase diagram. Every compound has a phase diagram, and the phase diagrams show us the solid, liquid, and gas phases of that compound. And it shows us which pressure and which temperature is needed to accomplish those physical states. For instance, at 760 torr, if it's at, let's say, that looks like approximately negative 90 degrees Celsius, it's going to be a solid state. At maybe 700 torr, and the temperature is up to 50 degrees, is going to be a gas state. So changing the pressure and changing the temperature can affect what physical state it is. And this chart tells us this. The line here is a sublimation line. It's to go from a solid to a gas and back again. The line here is the vaporization curve, to go from a liquid to a gas. And here is the fusion curve, to go from a solid to a liquid. In the middle you have the triple point, which is where all three phases can exist in equilibrium. And up here is supercritical fluid, this critical point. The highest temperature and pressure liquid phase can exist no matter how high the pressure. Let's take a look at the fact that this is specifically for water now. Notice that this curve right here, the fusion curve, is actually going inward. That's not typical. Typically, for a molecule, it'll be going outward like this way. It'll be going more in this direction. But water being so unique, and we're going to talk about the unique properties in the next tutorial, it's created a different phase diagram. And that's your introduction to the different states. Alright, so I actually like